Hitting on kinetics and equilibrium. Milks is here.
MoNaCo is 2.
All right. Video number 7.
Yep.
Almost done. We got pages 19 and 20, and might go into 21 actually now.
Yeah, doing some practice because we really wanted to show you.
We're going to guide you through some of this. Now, this is a concept, guys, that is muy importante.
Uh-huh.
Might take a little practice to get you.
We did in our last video what equilibriums were. And now we're going to show you how to predict which direction they shift when we manipulate them.
Okay.
And how we manipulate.
There you go.
So, here it is. How can you manipulate an equilibrium if the rates are equal and the concentrations are constant? So, as we said, it's a sealed container. How can you change it? Well, you could add things to the container. Pop the top on it, add one of the reactants.
Right. One of the products might be something that's valuable, so you start removing it.
Right, exactly. What if you're making chalk or something and you're taking it out? You know, you could add or remove heat, because as we know, heat is a reactant or a product in chemical reactions. Certainly going to. Or if it's a gas or gas is involved, you can increase or decrease the pressure, because as we know, for the kinetic molecular theory of gases, if I put pressure on them,
It's like increasing the concentration.
because I squeeze them closer together and you get more collisions occurring.
Right.
So kinetic molecular theory, collision theory are kind of connected in so much that they cause reactions to occur.
Right.
We're going to see whose idea it was to look at shifting.
Nice. And this one I can actually say, even though it looks really complicated. His name is Le Chatelier.
Yeah.
Le Chatelier, actually.
Yeah.
Le Chatelier.
French.
Le Chatelier. See, I even said
Got
I
that
could say it right.
silent R at the end.
Yeah. What this says is a reaction at equilibrium will respond to any stress in a way that returns it to equilibrium.
In so much, this is saying that chemical reactions are like people. We try to get away from what stresses us out.
Right.
We got to try and get back to our balanced, chilled state. So once a reaction reaches equilibrium, it wants to stay there. And so if you disrupt it by doing things like adding products or taking products, adding reactants, changing pressure or temperature, it's going to respond to re-achieve the equilibrium.
Correct.
So you will start to see a shift or a change. Maybe you'll see an instantaneous color change as it moves from one side to the other. You'll see more product being produced or more reactant being consumed. Basically, you stress out the reaction. It tries to get away from it.
Right. It really values equilibrium. Right. So it's going to do whatever it has to do to get back there.
Right.
Right. So now we're going to go through some quick notes about what we learned, how we figure this stuff out, and then we'll do some practice.
So the big overall rule, big idea,
Yeah, the overarching theme of how to figure this stuff out is this right here.
AA and TT.
TT.
Huh? What's that mean?
Well, the reaction is going to move away from what you add and towards what you take.
So you could either add something and it shifts away from whatever you had added,
Right.
or you could take something.
And the reaction will shift towards what you take.
Right. And we're talking about that, looking at the double-headed arrow in the middle
No.
and deciding which direction is it going to point to. If I take this stuff off the right-hand side,
Which is a product.
I took it away,
So it's going to move towards what I take.
The whole reaction would shift towards what you take and then make more stuff.
Right. So you initially take more product, but then the reaction itself makes more product.
In response to relieve the stress that you're taking something away,
Correct.
it's going to make some more.
Right. So let's give some quick examples, and then we'll get through some like real examples. So concentration. If I add reactants, remember reactants are on the left-hand side of the equation,
So you got to shift away from what you're adding.
which would now be to the right-hand side.
And we like to call that, there's two ways to say this. We can either shift towards the reactant side,
Yep.
or shift towards the product side. Or we can say shift to the right,
Or
which
shift
is
to
the
the left.
which is the product side.
Yep.
Or shift to the left, which is the reactant side. So
Correct.
there's two ways to be correct here when we're talking about which direction does it shift.
You just got to you follow this procedure and you'll get it right every time. It's pretty robust the way it's written so that it works for either side of the reaction, products and reactants, no matter what I'm adding or taking. Okay? Of course, if I take reactants themselves are on the left-hand side.
Take
So
them away.
I go towards what I take. The shift will go now towards reactants. So if I can identify with what I'm taking as a reactant, I know I'm going to go towards all the reactants.
Temperature. As we mentioned, we're going to say heat or temperature, which is the physical manifestation of heat,
We're going to
causes
treat it.
reactions to shift.
We're
And we
gonna
can treat
treat
it
it-
as a reactant or as a product.
There you go.
So an endothermic reaction absorbs heat. So the heat would be on the left side of the arrow.
Yeah, it would be a reactant.
It would be a reactant. So if we added heat, we're adding a reactant, and we're shifting away from what we had. So we shift to the right.
There you go.
If we take the heat away from an endothermic reaction,
Again, it's a reactant.
you're going to shift towards whatever you took away, so the reaction will shift to the left. And obviously, the vice versa is true.
Yeah.
So if you add heat and it's an exothermic reaction
I would shift left
instead of right,
because I'm taking
because the
or
heat
I'm
would be on
adding a
the
product.
side. Yeah,
Right.
right. Exactly. You'll
So-
see that when we get into the practice.
Yeah,
more definitely.
we kept this just to one side of the equation for the notes piece, but it is vice versa. Very good. So pressure. Now this one gets a little bit different because pressure isn't really a reactant or a product.
It just causes the reactants of the products to get more close to each other and follow collision theory
Right.
to make the other stuff.
So the general rule we do is, if I increase pressure, I'm going to shift towards less moles.
Of
Because
gas.
think about it, you got less space, so you might as well have less moles to fit into that
Right,
less
if you
space.
squeeze in stuff together, it'll combine to make a compound and it'll take up less space than it did when it was solo.
Right, and then if I decrease pressure, now I got a lot more room and a lot more space for all these guys to play.
Those
so
compounds
I can,
will pop apart and produce the individual elements that made them solo.
There you go. So now the overarching theme of this particular part of the notes is that if the reaction shifts to the product side, all the products increase.
In their concentration.
Correct.
So like if you had
Or
one
their
mole of a product and the reaction shifts to the right side, the product side, you're going to have more than 1 mole at the end.
Right, so you got more stuff.
The concentrations will change when you shift in equilibrium because it needs to reestablish the equilibrium. And then once it's reestablished, the concentrations are constant.
Right, and remember, concentration is how much stuff per volume. So
Right.
you get more stuff.
Exactly.
Okay, and then vice versa. If the reaction shifts to the reactant side, everything on the reactant side will increase.
Right. So you make more stuff on the reactant side, everything is what you make more of.
Right, and what's not written here then is the vice versa.
The concentrations
Of the other side go down. Okay, so now we're going to go through some practice and show you how this all works.
Noakes narrates, MoNaCo's right.
No, let's switch that up.
Oh, okay.
Yeah, let's switch it up.
All right, so for the first example, we have a reaction that does involve gases and heat. So we have 4 NH3s ammonia and 5 oxygen gases in equilibrium with nitrogen oxide and water and heat. So if we add H2O,
Okay, so now
gas,
So the first thing I want to do is find that.
right, there's the H2O gas,
And there it is.
and we're adding more of it.
So I'm going to go like this.
So
Arrow.
the rule is we shift away from what we add,
So
so
I'm going to shift to the
left.
left.
So you could say either
Left
reactants,
or draw an arrow, or reactants.
it's either way, and the concentration of NH3,
So now I got to find that.
oh, there it is, and since we're shifting to the left, that concentration will go up, as well as the O2s. So the concentration of NH3 will go up. Okay. That's how we do. We draw arrows, we look at a reaction, we identify the products and reactants that are involved, and we just push arrows. That's what we're doing.
It's really
Pushing
what this
arrows.
is, you know.
So if we add O2,
All right, let me find it. O2, oh, got it.
got it, the equilibrium will shift to the
So I'm adding O2
away from what you add,
away from what I had, so I got to go to the other side of the arrow.
so the equilibrium shifts to the right, or the product side, sorry. And the concentration of NO, let's find NO, there it is. Let's see, it's on that right-hand side of the arrow, so it'll go up along with the amount of heat and the amount of water that is produced.
Good.
Cool. So if we add some H2O gas,
Okay, that's, oh, whoop.
nope, that's no gas. Literally, NO, nitrogen oxide.
There it is, got it.
So we add H2O gas. Equilibrium is going to shift away from what you add. So it's left, shifting to the left or to the reactant side. And the concentration of NO, it goes down along with the amount of H2O and heat.
This
Because
is where
the
it
reaction shifted away from that right-hand side. Whatever you shift away from drops in concentration.
Right. Right, so we can't get confused that we added water gas, water vapor, and then all of a sudden the concentration of water vapor went down.
Right.
Well, it's because there's that. It's just
You added it, and then it reacted because it has to be reacted in order to reestablish the equilibrium.
That's the piece we're looking.
Okay. So last one, we're going to add some nitrogen oxide, nitrogen monoxide.
And got it. I know
And
gas.
which direction? We added it.
All right, so I got to go away from what I had.
Yep. So it's going to shift to the left.
Okay.
Which concentration would decrease? Which concentrations would decrease?
Well, if I'm shifting to the left, shouldn't everything on the left increase?
Everything on the left goes up, and that means everything on the right goes down. Even though we just added a little more NO, after it's done reacting, the concentration goes down. And the heat. So this reaction would actually get colder.
Right. We'll see. A lot of times you'll see heat as like plus kilojoules.
Yeah.
Maybe plus 600 kilojoules.
My turn.
Oh, hey, goody good. All right, erase all that.
Yeah.
First, erase all that. And then we have a different equation. I do see right off the bat that kilojoules as a reactant. I see that 2804 kilojoules as a reactant.
So that means
That's heat. And
well, what am I doing here? What am I supposed to do?
it says if I remove water, the equilibrium will shift. So first of all, remove means take.
I got to find water.
Yep. And let's remember, remove means take. So, and then the saying says I move towards what I take. I took a reactant, so I should go towards the reactant side. So I shift left.
To the left.
And then it wants to know what happens to the concentration of sugar.
Well, if I'm shifting to the left, the concentration of sugar's got to go down.
Because I'm shifting to the left, so everything on the left-hand side should go up.
The amount of heat, carbon dioxide, and water goes up, but sugar goes down and oxygen goes down.
Yeah, I hope you guys are good and thoroughly confused right now. But you see the patterns actually, the pattern's still the same, right? Cool.
Example 2, this is a funky equation. I forgot to tell everybody what this equation actually is for. You recognizing this mix?
Carbon dioxide and water
And heat
makes sugar and oxygen. It really looks like a reverse combustion reaction to me.
But it's, yeah, it is. It's called photosynthesis.
Oh, nice.
Photosynthesis.
Nice.
Chlorophyll? More like borophyll.
Why you gotta make me laugh during videos
Sorry.
like this? Killing me. Erase that stuff. Let's do this next one. And I want you guys to follow this process because this process that we're doing works every time. Ready? So if I'm going to remove or take oxygen gas, first find the oxygen and then remove it. And then I go towards what I take. So now, because it's a product, I need to go towards the product side. And then it says, what's going to happen to my sugar concentration again? If I go towards the products, all the products should increase.
Yep.
You got to put an increase on it, O2 too, or it's going to look really confusing to me.
Yeah.
Okay? All right, good?
Yeah.
Next one. Try to get through this video before 35 minutes. If I remove CO2 gas, remember, remove is take, CO2 gas is on the reactant side. I'm going to move towards what I take. So I'm going to shift to the left. That means everything on the left goes up and everything on the right goes down. And the question asks for O2 gas, which is on the product side, it goes down. Good. Now, if I remove or take sugar, well, let's find that sugar. We made some sugar and I want to take it. I need to, the equilibrium will go towards what I take. And then which concentrations would, does that say increase or decrease? Decrease. So if I'm moving towards the right, everything on the right will increase. Therefore, everything on the left will decrease.
So that would be
Carbon dioxide gas and liquid water.
there it is.
All right. So this is basically what happens when I change concentration.
Right.
Okay, but there's some other factors we can change. Okay?
Temperature.
Temperature.
Here's your Miss Milk.
Oh, yay.
Writing. So, simpler questions, but there's, if we added more heat.
Gotta find heat.
Oh, they're easy. So we add more. That's going up. Which direction would the equilibrium shift?
Away from what I had.
So it would shift to the left. Which concentrations would decrease?
Right,
Well,
so everything on the right then has got to go down.
right. And which concentrations would increase?
So I'm going to say decrease equals NO gas, H2O gas, heat.
Which concentrations would increase?
The increase is going to equal everything on the reactant side.
NH3.
NH3 and O2.
Good.
Good. Oh man, sorry, it's so sloppy.
Super sloppy. It's like MoNaCo's handwriting.
Oh.
If we are looking at example number 2 and heat's involved, we're going to
Are we
add
switching?
My turn.
Okay, we're switching. Let's see if we can write a little neater than me. I set him up for success. There's the heat. Identify the heat. Notice this time it doesn't say heat. It's written in kilojoules.
So we're going to add some more heat.
All right, so if I add heat, I move away from what I add.
Shift
So,
it to the right.
so now everything on the right goes up, and everything on the left goes down.
Concentrations would decrease. Well, these ones would drop. And these ones would go up.
There you go.
So, let's see. Decrease.
Decrease first. Carbon dioxide gas.
H2O. And heat.
There you go.
Which concentrations would increase? Well,
Methane gas, CH4.
and oxygen.
Oxygen gas. There we go.
Simple enough. Away from what you add, towards what you take. Concentration.
And this is the application thereof.
Concentration shifts depending on which side you move to.
Yeah, and these acronyms that we're starting to put out there for you guys, guess what? For the rest of the year, we're going to be using a lot of these acronyms.
So this is for gases only. And this example, pop quiz, what type of equilibrium is that, Mr. Milks?
Looks like phase.
But, is it?
I don't know.
Is aqueous really a phase of matter?
No. Oh, it looks like maybe what's going on in the top of my soda can.
Solution equilibrium.
Yeah, I mean, when my soda can is sealed, this is what's going on.
Right, you've got carbon dioxide gas in there and dissolved carbon dioxide gas. So this is a solid, well, this is a solute, that's gas, that's behaving as if it was like a solid for solution equilibrium. So this is really a solution equilibrium.
It is. And it's not gas on both sides. So that mole thing that we had going on that we'll use in the next page is not necessarily, So but we're trying to think about it a little bit.
Which direction will the equilibrium shift? So if I increase pressure.
On a gas, do you think the gas is going to go into the liquid more?
Yes.
Yes.
So it's going to shift to the right.
Right.
What will happen to the concentration of the CO2 aqueous?
Increase.
It goes up.
So if I shift to the right, everything on the right has to go up. The pressures increase, which direction will the equilibrium shift? We just did that to the right. What will happen to the concentration of CO2 gas?
So it shifts to the right.
So if it shifts to the right, the CO2 gas has got to go down.
Right.
Because it's on the left-hand side.
So now we're going to decrease some pressure. Which direction will the equilibrium shift? So it's going to decrease the pressure. So the aqueous CO2 is going to come out of solution and become a gas.
It's got more space.
To the left.
So it's going to shift to the left now.
What will happen to the concentration of CO2 aqueous? It's going to go down.
It's going to go down. It's on the right-hand side, and we're shifting left.
Right. And so if the pressure is decreased, we know it's going to shift to the left. What will happen to the concentration of the CO2 gas?
It's going to go up.
Through the roof. Moving on. I got to finish up quick here.
Sorry it's been so long, guys. But this is muy importante. We know about the hang-ups that we're going to have.
So here's the situation where we have
the moles.
Yes.
Gas is all the way throughout.
Mm-hmm. So if we increase the gas, which direction, pressure on the gas, which direction is this equilibrium going to shift?
Well, this rule said if I increase the pressure on gases, I'm going to go towards less moles.
Right. So on the left side of the reaction, I see I have 1 mole of N2 and 3 moles of H2. So I have 4 total moles.
Yep. And on the product side, I only have 2. So I'm going to shift towards the product side. So go ahead and write an arrow up top there. I'm going to shift to the right.
Shift to the right. What will happen to the concentration of your NH3?
Well, if I'm shifting to the right, it's on the product side. It's going to go up.
Right. So if the pressure is increased, which direction will the equilibrium shift?
Again, to the right.
To the right, because there's fewer moles over there.
And what's going to happen to the N2 gas?
Well, N2's on the left-hand side.
So if I'm shifting to the right, everything on the left goes down.
Drops it.
There you go.
If the pressure is decreased.
Now this is opposite direction.
Right.
So if I decrease the pressure, I'm going to move towards the more moles. So now I'm going to go left.
Right.
Okay. And so
NH3 gas
is on the right-hand side.
So it's going to drop.
It's going to drop. It's going to go down.
And if the pressure is decreased, which direction will the equilibrium shift? We know.
Again, to the left.
What will happen to the concentration of H2?
Well, if I'm shifting to the left and H2 is on the left,
You're going to go up.
there you go. It's going to increase. Now, notice we didn't write any of that part down.
Because we want to see if you're paying attention.
Please, guys, this isn't meant to trip you up. This is meant to make sure you're paying attention. I'm sorry this video took so long, but to be honest with you, we know from teaching the course, this particular piece can be a big-time hang-up if you didn't have some proper instruction on all the different ways that can stress an equilibrium.
Remember, away from what you've added,
Towards what you take.
concentrations change. If you're shifting away, whatever you're shifting away from drops.
And when if you're shifting
Towards, whatever you're shifting towards increases.
yes, everything on that side of the arrow,
Everything, heat included.
heat included.
The hardest part of this is the gas.
Yeah, so we actually went through most of the practice for you guys. Got one more practice page. Let's see if after watching this video you can do this Le Chatelier.